Look closely at a vehicle's side mirror next time you're on the highway. A car directly behind you looks small and distant, yet the mirror somehow captures 3 full lanes of traffic at once. Why does this glass shrink the objects in your wake while simultaneously expanding your total view of the road? The secret is in the physical shape. This is a convex mirror, defined by a reflecting surface that bulges outward toward the light rather than lying flat. While we often associate curved glass with the magnification found in a dental mirror, the convex geometry is built to do the opposite. It strictly reduces the size of everything it reflects. The outward bulge functions as a compression tool, fitting an expansive, wide-angle environment into a manageable, upright frame. When parallel light rays strike a flat mirror, they bounce back at the same angle they arrived. But on a convex surface, those same rays hit a curve that is angled away from the center, causing them to scatter. This scattering action is known as divergence. Instead of meeting at a point, the light rays spread further apart the further they travel. To interpret this, your brain traces these spreading rays backward, acting as if the light originated from a single point hidden behind the surface of the mirror. This intersection is the virtual focal point, creating what we call a virtual image. A virtual image is an optical reconstruction that appears to exist behind the mirror, meaning it cannot be projected onto a physical screen. Because the light rays never actually meet in front of the glass, the image you see is a geometric projection happening entirely inside the mirror's world. As an object moves in front of this curve, the reflection follows 3 absolute geometric rules that never change, regardless of distance. First, the image is always erect, or upright. Second, it is always reduced. The reflection will always be smaller than the actual object. Finally, the image is always virtual, remaining permanently locked behind the mirror surface. This reduction in size is a calculated trade-off. By shrinking the objects, the mirror can gather light from a much wider angle than a flat surface ever could. This massive field of view is what allows a driver to see across several lanes of traffic at once, effectively eliminating the blind spots that lead to accidents. The shrunken image is the essential feature that buys the wide-angle perspective required for safety on the road. Light follows fixed geometric paths, whether it bounces off a reflective coating or travels through transparent glass. Consider the concave mirror. Its inward curve forces parallel sun rays to converge or come together at a single point, generating massive thermal energy. A convex lens achieves this same intensity through refraction. Refraction is the bending of light as it passes from one material into another, in this case, from the air into the thick center of the glass. Geometrically, the concave mirror and convex lens are twins. Even though they use different materials, they both force parallel rays to meet at a real focal point. When 2 optical tools share the same behavior, like convergence, they are functionally identical. This brings us back to our convex mirror, which, as we've seen, is defined by its ability to diverge light. Its twin is the concave lens, a piece of glass thinner in the middle than at the edges. When light passes through it, the glass bends the rays outward, causing them to spread apart. Because they both diverge light, they create the exact same results. Whether you use a mirror or a lens, the image will always be upright, smaller than life, and virtual. Understanding this geometry allows us to manipulate our surroundings and expand our vision. Whether light is bouncing off a curve or bending through it, the rules that govern our sight remain constant.